If a linear has no solutions, a linear system has no solutions, it is called inconsistent. We had some people read. Very good. Okay. Now, what are the 3 elementary row operations? You can either give the names that the book gave, or if you can just describe the 3 things. Replace, interchange, and scale. Sure. Interchange and scale. Scale 1C. Okay. So replacement, that was you can replace any row with itself plus a multiple of another row. Interchange was you can always swap the locations of 2 rows, and scale is you can multiply a row by a scalar, by any number, not by a non-zero constant. Yeah, thank you. Yep. Do you have to do these in any particular order? No, you can do them in any order you want. Yep. Okay, the matrix right here, this 1, 0, 0, negative 2, 3, 0, 4, 2, negative 5 is in a special form. What's it called? Triangular. You can't tell if it's augmented unless you know the associated system. It's triangular because we have zeros in a triangle on the bottom. If you have zeros in a triangle on the top, that's also called triangular. Right? This one is called lower triangular. There's also upper triangular. Okay, so very quickly about the quizzes. So today we're going to cover the material that you read about in preparation for class 1.1. We're going to review how to use the method of elimination to solve a system of linear equations. And then next, we're going to learn a new method for solving linear systems that uses matrices. All right, so when solving a system of linear equations by elimination, there are 3 basic steps that you're allowed to do. You can replace one equation by the sum of itself and a multiple of another. You can interchange 2 equations. You can multiply all the terms in an equation by a non-zero constant. All right, so this is just totally algebra review. I'm sure you all learned this in a previous course. I want to solve this system that has 2 equations, 2 unknowns. X plus 5y equals 7. Negative 2x minus 7y equals negative 5. I want to solve it using elimination. What do I do?
Multiply the top by 2.
Multiply the top equation by 2. So this is going to become 2x plus 10y equals 14. Keep the bottom equation the same. Add them together. The x's go away. And you're left with 3y equals 9. So y equals 3. Right? And then how do you get x? Plug it into either of your 2 original equations. So you have x plus 5 times 3 equals 7. I'm just plugging into that first equation. So 7 minus 15 is negative 8. So feel everyone's comfortable with that? Okay, good. All right, so in the above system, this guy up here, okay, all the important information is contained in the coefficients and the constant term. The names of the variables are unimportant, right? I could have used a and b instead of x and y. It's the exact same system. Okay, so we can represent the system using a rectangular array called a matrix. So in the first column, we put coefficients on x. So for this system, I would have a 1 and a negative 2. Second column, I put the coefficients on y, which would be a 5 and a negative 7. And then in the last column, I put the constant terms that are on the other side of the equal sign, 7 and negative 5. So that matrix we just created, we say it has dimensions 2 by 3 because it has 2 rows and 3 columns. So it always goes rows, columns when you are stating the dimensions of a matrix. All right, so when you're solving a system using a matrix, you can perform the same basic maneuvers on a matrix that you do on the equations that we did earlier, right? So you can replace one row by the sum of itself and the multiple of another row. You can interchange two rows, and you can scale a row by a non-zero constant. So I'm going to solve our original system using the matrix operations that are going to kind of mirror the approach we did when we did it like the old-fashioned way. Yep.
I've seen matrices written, so it's just the coefficients on the x and y in one matrix, and then there's another matrix containing the constants.
So it's not actually another matrix. Sometimes you see some textbooks, and it's quite common, will put a vertical line here to separate the coefficients from the constant terms, but it's still considered one matrix. Yeah. So yeah, if you Google any of this stuff or Khan Academy or whatever, you'll probably see the vertical line. Okay, so I'm going to solve the original system using the matrix and row operations. So I start by writing down my original matrix: 1, -2, 5, -7, 7, -5, vertical line. Okay, vertical line is optional. Yep. Yep, it's just to help you kind of remind you what this is representing, that the last row is the constants. Okay, so I'm going to perform a row operation, right? So I'm going to turn this into a new matrix, and I'm going to want to make sure I mirror what we did earlier. Okay, I am going to replace row. Okay, so the first thing we did is we multiplied the first equation by 2, right? I multiplied the first equation by 2. So that's going to be my first thing. I'm going to scale row 1. Okay, so I'm going to do 2 row 1 becomes my new row 1. So 2 row 1 becomes the new row 1. Okay, so my new row 1 is going to be 2, 10, 14. Row 2 stays exactly the same: -2, -7, -5. Okay, so my next step was I added the two equations together, right? I'm going to add the two equations together, and that's going to become my new row 2. So row 2 plus 1 row 1, right? Because my row operations say you can add a row to a multiple of another and use it to replace. So row 1 plus 1 row 2 becomes my new row 2. So row 2, I'm going to replace row 2 with 1 times row 1, with itself times plus 1 times row 1. So -2 plus 2 is 0. -7 plus 10 is 3. -5 plus 14 is 9. Now row 1 remains unchanged here. Row 1 is involved, right? I'm adding it, but it does not change, right? I'm just using it to change row 2. So row 1 just gets copied. Okay, so now at this point, I have eliminated a variable, right? I have a 0 in the x column. So I can translate this to a set of equations that says 3y equals 9 and 2x plus 10y equals 14. And then I can back substitute, right? So this says y equals 3, put a y equals 3 in here, and I get 2x plus 30 equals 14. So x equals -8. Yes.
Now, you basically scaled on the outside with 3y, but on the inside matrix, could you?
Yes, absolutely. I could have done one more matrix operation here and scaled row 2 by 1/3. Yep. And then I would have, when I translated to an equation, it would have just said y equals 3. Yep. You don't have to, but what we're trying to do is create an algorithm like that you could program a computer to do. So Sometimes the more efficient thing is obvious to you, but you want to write something that a computer just can always follow. Yeah. All right, so with a single unknown, we've always been calling it X, forever. 2 unknowns, we typically use X and Y, and with 3 unknowns, we use X, Y, and Z. But after 3 unknowns, we've run out of letters, right? So as a matter of common practice, we use X sub I as the name of each unknown, and I will go from 1 to however many unknowns we have, right? So for 3 unknowns, instead of X, Y, Z, we would use X1, X2, X3. So here's your general algorithm, right? This is how you solve using a matrix and row operations. Use equation 1 to eliminate x1 from all equations below it. Or use row 1 to eliminate all entries in the first column below row 1. Then use equation 2 to eliminate x2 from all the equations below it. Or use row 2 to eliminate all entries in the column in the second column below row 2. Okay, and then you just keep going like that until you hit a triangular form. Okay, so you have a triangle of zeros in the lower left, and then you back substitute. All right, so I didn't do a very complicated problem with you, but I have my first problem that I set up for you to do. I gave you step by step what row operations to do, and I'm going to have you just try and do it on your own.